Hi everyone, I'm Jesus Perez Martin, and today I'm going to talk about how to improve video captioning with temporal composition of a visual-syntactic embedding. This work is done in collaboration with Benjamin Bustos and Jorge Perez. The goal of video captioning, or sometimes called automatic video description generation, is to describe the content of a video with natural language sentence. So, for example, given the following video, the goal is to generate something like the men are fighting using martial arts, or the men are doing martial arts together in the field. Or in this another video, some possible captions could be: a woman is applying makeup on her face, or a girl applying blush on her face. As we can see in red, it is very common to use the same syntactic pattern for describing the content in the video. Based on that, we claim that cues about the syntactic structure of the video's descriptions can be directly extracted from the video. Also, we notice that existing models often produce syntactically incorrect sentences, which harms their performance on standard datasets. So, let's move on to the model. The first stage consists of extracting 2D CNN and 3D CNN feature vectors. Then, these features are concatenated and averaged to produce a global representation of the video. The second stage in our encoder consists of producing a semantic representation of the video by using a standard multiclass classifier that gives probabilities of possible keywords that are relevant to describe the video. And the third stage in our encoder produces what we call visual-syntactic embedding. Then, given these three representations, our decoder network generates a natural language descriptions combining them. Now, I'm going to explain the main intuition and how the visual-syntactic embedding is constructed from the data. We attack this representation learning problem as a part of a speech template retrieval problem. The aim is to learn two mapping functions that map from visual features and POS templates to a joint embedding space. In the learning process, we ensure that the encodings of a video and the positive descriptions are quite similar to each other, while the encodings of a video and the negative descriptions are very different. Having this, we define the language model as a recurrent architecture that generates the tokens each word at a time. This recurrent architecture has four components to dynamically combine the three encoder representations. Firstly, three specialized recurrent layers based on compositional LSTM network combine the representations by pair. As we can see, these layers, different to other models, are not deeply connected. Next, a hierarchical fusion strategy fuses the output of three recurrent units before generating the word in each step. This process is repeated until the end of the sentence. So, for training the model, the concept detector is pre-trained using classification loss. The visual syntactic embedding is pre-trained using triple ranking loss. And for the language model, we propose a syntactic weighted language loss. For the experiments, we compare our approach to the state-of-the-art methods on the standard splits of MSVD and MSRBTT datasets. On MSVD, these charts compare our proposal to recent approaches from ICCV and CVPR. Specifically, the ICCV approach also considers the syntactic structure, but without considering the temporal relations between the visual and semantic representations. On MSRBTT, our approach also surpasses the three methods for all metrics except CDR, where the ICCV work reaches better score by directly reinforcing this score. Going back to examples I showed you before, we can see that our model generates a more accurate description. Here I highlighted some words and tags where the model combined the semantic and syntactic information correctly and didn't misgenerate the last words as eyeshadow. Here is another example in which we recognize the syntactic pattern correctly, and you can notice the difference with the ablated model without using syntactic representation. For more details, we have released our code, pre-computed features, and training models. Thank you very much for your attention.